scientists made a major breakthrough.
Brought Germany's revolutionary fusion machine. It's a tense moment.
Germany just dropped a fusion bomb. Not literally, of course. Their new reactor design threatens to steal the spotlight from even the mighty ITER project, promising a future fueled by clean, endless power. But what exactly makes this German marvel tick? What scientific sorcery allows it to achieve the seemingly impossible? Fusion energy, a quest for clean and limitless power. Nuclear fusion, the process of fusing lighter atomic nuclei to form heavier ones, stands as a powerhouse for energy production, mimicking the very mechanism that fuels the sun and stars. Since the early 20th century, when scientists unraveled the fundamental principles of nuclear reactions, the potential to harness this power for peaceful purposes has captivated them. However, achieving controlled fusion reactions on Earth has proven to be a formidable challenge, demanding extreme conditions of temperature, pressure, and magnetic fields to sustain a plasma, a state of matter crucial for fusion to occur. The story of fusion research is a captivating saga, woven with both breakthroughs and setbacks, international collaboration and competition, all tinged with drama and intrigue. The initial forays into fusion experimentation date back to the 1930s, as physicists bombarded light elements with accelerated particles, witnessing the birth of new isotopes and neutrons. By the 1940s, fusion took on a more ominous role, fueling the creation of thermonuclear weapons and unleashing catastrophic power through fusion-fueled explosions. The post-war era brought a shift in focus. With the declassification of the hydrogen bomb's secrets, doors opened to explore fusion for peaceful energy production. Various confinement and heating methods were devised, including the pinch, the mirror, the stellarator, and the tokamak. Among these, the tokamak, a donut-shaped magnetic configuration pioneered in the Soviet Union, emerged as the most promising design. Through the decades, nations like the United States, the United Kingdom, France, Japan, and China refined the tokamak concept, inching closer to the elusive break-even point where fusion power equals input power. The 1980s witnessed the construction of larger and more powerful tokamaks, such as the Joint European Torus, or JET in the UK, and the Tokamak Fusion Test Reactor, or TFTR in the US. The JET, for example, was a trailblazer, operational from 1983 to 2023. This tokamak, a donut-shaped machine that confines plasma with magnetic fields, aimed to pave the way for future commercial fusion power plants. JET's success story is undeniable. By 1993, it had shattered records for its size, becoming the first device to achieve controlled fusion using a deuterium-tritium fuel mix, the same reaction future power plants will likely rely on. This achievement solidified the scientific potential of fusion energy. These endeavors achieved unprecedented levels of fusion power and plasma performance. Yet technical, financial, political, and environmental hurdles loomed large. Amidst these challenges, the late 1980s saw the birth of an ambitious idea, an international collaboration to pool resources, share risks, and collectively pursue the scientific and technological promise of fusion energy. Thus, the International Thermonuclear Experimental Reactor, or ITER, was conceived, uniting unlikely partners like the European Union, the United States, Russia, Japan, and China, with India and South Korea later joining the consortium. The ITER project aims to demonstrate the feasibility of fusion as a sustainable energy source, propelling fusion energy to the brink of industrial application. The ITER reactor is designed to generate 500 megawatts of fusion power for at least 400 seconds, achieving a tenfold gain in plasma heating power. This milestone would mark the first instance of a fusion device achieving a burning plasma, where self-heating from fusion reactions surpasses all other forms of heating. Moving beyond the early struggles, ITER is enhanced by creative design elements. So what does the ITER project have at its core? The ITER project revolves around the tokamak principle, enhanced by innovative design elements. With a major radius of 6.2 meters and a plasma volume of 840 cubic meters, the ITER tokamak stands as the largest and most complex fusion machine ever constructed. Employing superconducting magnets, the ITER tokamak generates a powerful magnetic field, reaching 5.3 Tesla externally and up to 6 Tesla internally, crucial for confining and shaping the plasma. To heat and control the plasma, the ITER tokamak utilizes a diverse array of heating and current drive systems, including neutral beam injection, radio frequency waves, and electron cyclotron waves. The fusion fuel employed consists of a mixture of deuterium and tritium, two isotopes of hydrogen. Deuterium is readily available in nature, while tritium is produced within the ITER reactor itself, facilitated by lithium blankets surrounding the plasma that absorb the neutrons generated by fusion reactions. Now the question arises, where is all of this groundbreaking stuff even happening? Well, the ITER project is taking shape in Saint-Paul-les-Durance, France, adjacent to the Cadarache facility, one of Europe's largest nuclear research centers. Initiated in 2010 after years of negotiations and groundwork, this colossal endeavor involves thousands of scientists, engineers, and laborers from 35 different countries, alongside hundreds of companies and institutions. With an estimated cost of around $20 billion, the ITER project is set to reach completion by 2025, marking the milestone of achieving the first plasma. It's a global collaborative effort, representing a $22 billion science experiment uniting numerous nations. Upon achieving the first plasma, the ITER project will embark on a 20-year operational phase. During this period, researchers will conduct a series of experiments and tests to refine plasma performance and demonstrate the integrated operation of the fusion reactor. Additionally, the project will serve as a stepping stone towards the next phase of fusion energy development, the demonstration reactor. This next-generation reactor aims to harness fusion to produce electricity on a commercial scale. Now let's get into the more technical side of nuclear fusion. Nuclear fusion occurs when two hydrogen isotopes, like deuterium and tritium, are brought into close proximity. Overcoming their natural repulsion, they fuse to form a heavier helium nucleus. This fusion reaction releases a substantial amount of energy, primarily in the form of high-energy neutrons and gamma rays. The energy released is determined by the mass difference between the initial and final nuclei, as described by Einstein's famous equation, E is equals to mc squared. In the deuterium-tritium fusion reaction, this mass difference translates to a staggering 0.7% of the initial mass being converted into energy. This means that even a small amount of mass can yield a tremendous amount of energy. However, achieving nuclear fusion is an extraordinarily challenging task. To initiate fusion, the hydrogen nuclei must be heated to extremely high temperatures, around 100 million degrees Celsius, to enable them to move fast enough to collide and fuse. Additionally, they need to be confined and compressed to a high density to sustain the reaction. These demanding conditions, known as the Lawson criterion, necessitate significant energy and technological capabilities. But there's a lot more to the picture than plain old nuclear fusion. The art of magnetic confinement fusion. Magnetic confinement fusion utilizes powerful magnetic fields to control and sculpt the scorching hot fusion plasma, preventing it from touching the reactor walls. These invisible shepherds not only confine the plasma, but also lend a hand in heating and compressing it, significantly boosting the odds of successful fusion reactions. One of the most refined designs is the tokamak, shaped like a donut. It generates a toroidal magnetic field by channeling a large electric current right through the plasma itself. This electric current acts like a conductor, generating a magnetic field that encircles the plasma. Another set of coils strategically placed around the plasma weaves a twisted poloidal magnetic field. The marriage of these two magnetic fields results in a helical field, providing crucial stability for the plasma. As mentioned before, the tokamak design forms the bedrock for the ITER project, a global collaborative effort pushing the boundaries of fusion research. The Stellarator, another promising contender, shares similar goals with the tokamak, but takes a more intricate approach. Unlike its donut-shaped counterpart, the Stellarator boasts a more complex shape and ditches the plasma current for magnetic field generation. Instead, it relies on meticulously designed twisted coils to create the optimal magnetic field configuration. One significant advantage of the Stellarator is its ability to operate continuously, eliminating the risk of plasma disruptions that can plague tokamaks due to instabilities in the current. Germany's Wendelstein 7X project champions the Stellarator design. Its ambitious goal? To demonstrate the viability of a Stellarator as a full-fledged fusion power plant by achieving record-breaking plasma densities, temperatures, and confinement times. A key distinction between these two designs lies in their approach to generating the magnetic field. Tokamaks rely on the plasma current for part of the field, while stellarators take a fully external approach. This eliminates the need to induce or maintain a current within the plasma, significantly reducing the risk of instabilities and disruptions. Additionally, stellarators can operate continuously, offering a potentially more stable and predictable environment for fusion reactions. The stellarator concept, first proposed in 1951, initially faced challenges due to the complexity of the magnetic coil shapes and maintaining plasma stability. Research in the US waned, but continued advancements in Germany and Japan led to innovative designs and a resurgence of global interest. Recent decades have witnessed a renewed focus on stellarators, fueled by advancements in computational power, engineering techniques, and our understanding of plasma physics. A breakthrough discovery was the concept of quasi-symmetry, a property that helps minimize energy losses and enhances plasma confinement. Achieving this feat requires sophisticated optimization algorithms and supercomputers. Several new stellarator devices, including the record-breaking Wendelstein 7X, have been built to test quasi-symmetry and delve deeper into stellarator physics. The Wendelstein 7X, with its complex magnetic coils, aims to showcase the potential of stellarators as future fusion reactors. Magnetic confinement fusion, with its diverse approaches like tokamaks and stellarators, represents a powerful strategy for harnessing the immense energy potential of fusion. While challenges remain, the continuous advancements offer a glimpse into a future powered by clean and limitless energy from the stars. Inertial confinement fusion. Inertial confinement fusion offers an alternative approach to harnessing the power of fusion. Here, powerful lasers or particle beams act as the shepherds, heating and squeezing a tiny pellet containing the fusion fuel, typically a mixture of deuterium and tritium. The aim is to ignite the pellet, triggering a fusion reaction. The intense radiation pressure from the beams compresses the pellet, creating a shock wave that surges inwards. This surge dramatically increases the temperature and density of the fuel, eventually leading to a burst of energy and neutrons released from the core of the pellet where fusion occurs. The primary challenge in inertial confinement fusion lies in achieving a symmetrical and uniform implosion of the pellet. Precise and synchronized delivery of the beams is crucial for success. Additionally, the implosion needs to be incredibly fast to overcome heat loss and pressure caused by thermal conduction and hydrodynamic instabilities. One advanced design for inertial confinement fusion is the Hull Realm, a hollow cylinder that houses the fuel pellet. So what is it, and how does it assist the process? Laser beams pierce through openings at the ends of the Hull Realm, irradiating its inner wall. This intense heat causes the inner wall to emit X-rays, which uniformly implode the pellet. The Hull Realm concept serves as the foundation for the National Ignition Facility, or NIF project, boasting the world's most powerful laser. NIF aims to achieve ignition, a self-sustaining fusion reaction, by delivering over 1.8 megajoules of ultraviolet laser energy to a whole realm in mere nanoseconds. Since its ignition experiments began in 2010, NIF has achieved remarkable results, including record levels of neutron yield, fuel density, and energy gain. The Z-pinch presents another innovative approach to inertial confinement fusion. This device utilizes a powerful electric current to generate a magnetic field that compresses a plasma column along its axis. The plasma column, formed using various methods like a thin wire array, gas puff, or liquid jet, is then driven by a pulse power generator, or capacitor bank. The Z-pinch can produce extreme temperatures and densities, while also serving as a source of X-rays, neutrons, or ions. The Z-machine project in the United States stands as the world's most powerful pulse power generator experiment, and it utilizes the Z-pinch concept. The Z-machine delivers up to 26 megajoules of electrical energy to a Z-pinch load, creating plasma conditions relevant for fusion research and other applications. The Z-machine has demonstrably produced high-quality X-rays for driving Hull realms and fuel pellets, alongside generating fusion neutrons. Fusion research, a collaborative quest for clean energy. Fusion research stands as a global endeavor, holding immense promise for a clean and sustainable energy future. At the forefront of this exciting field lies the Max Planck Institute for Plasma Physics, or the IPP, a leading European hub not only for Germany, but for the entire continent. IPP boasts two significant facilities, the Aztecs Upgrade Tokamak in Garchin and the Wendelstein 7X Stellarator in Greifswald. These facilities serve as vital platforms for IPP's groundbreaking research in various aspects of plasma physics, the foundation for achieving fusion. For decades, IPP has made significant contributions in areas like magnetic confinement, a method for controlling scorching hot plasma using powerful magnetic fields, plasma heating, crucial for initiating fusion reactions, diagnostics, which provide vital insights into plasma behavior, and plasma control, ensuring stability within the reactor. Beyond its own research, IPP plays a pivotal role as the program management unit of Eurofusion, the European consortium for the development of fusion energy. This consortium unites 30 fusion centers across 25 European Union countries, as well as Switzerland, Ukraine, and the United Kingdom. Eurofusion serves as a powerful force for coordination, fostering collaborative research activities across the continent. This spirit of collaboration extends beyond Europe, with IPP actively partnering with other players in the fusion research field. A prime example is Gauss Fusion, a company aiming to bridge the gap between research and commercialization. Gauss Fusion benefits from IPP's extensive network and infrastructure, leveraging the Aztecs Upgrade Tokamak for its projects. While IPP focuses on advancing the scientific understanding of fusion, the complementary efforts of companies like Gauss Fusion demonstrate the diverse landscape of the fusion research field. But as with anything, there are some challenges facing fusion research. Are there any potential solutions? Or will they be figured out along the way as this technology is developed further? One of the major challenges facing fusion research, including projects like ITER, is the availability of tritium, a rare and radioactive isotope of hydrogen essential for fueling fusion reactors. While ITER will initially rely on external sources of tritium, companies like Gauss Fusion are exploring innovative solutions for self-sufficiency. Their approach involves advanced tritium breeding modules that utilize neutrons from fusion reactions to produce more tritium from lithium, creating a closed-loop fuel cycle for future fusion power plants. Gauss Fusion takes a distinct approach compared to ITER's experimental focus. Their ambition lies in building and operating commercially viable fusion reactors capable of generating electricity and contributing to the energy grid. These reactors aim for seamless integration with existing infrastructure, operating continuously and reliably to meet energy demands. Efficiency and sustainability are paramount to Gauss Fusion's vision. They plan to achieve high power output and efficiency by utilizing high field magnetic confinement fusion and optimized plasma parameters within their tokamak designs. While leveraging existing tokamak technology and infrastructure is crucial, the success of Gauss Fusion in the field of fusion research as a whole hinges on attracting top talent from diverse scientific backgrounds. Building a robust foundation of expertise and leadership will be essential for overcoming the remaining hurdles on the path to clean and abundant fusion energy. Gauss Fusion's impressive strides in the fusion research landscape wouldn't be possible without the guidance of a formidable supervisory board. This esteemed group brings together diverse expertise from various fields, shaping the company's strategic direction and propelling its vision for commercial fusion. The Stellarator, a promising path to fusion energy. Another approach to achieving fusion involves stellarators, a type of device that utilizes intricate magnetic fields to confine superheated plasma. This document delves into the history and advancements of stellarator research, highlighting its potential and challenges. The journey towards optimized stellarators began in Germany at the Max Planck Institute for Plasma Physics, or IPP, located in Garching. The IPP is an institute of the Max Planck Society, part of the European Atomic Energy Community, and an associated member of the Helmholtz Association. The IPP's creation, the Wendelstein 7S, operational from 1988 to 2002, marked a significant milestone, exceeding expectations. By 1993, it had surpassed all previous records for machines of its size, establishing a new benchmark for performance. Inspired by this success, researchers at the University of Wisconsin-Madison embarked on a mission to develop the first fully optimized stellarator. Their efforts culminated in the helically symmetric experiment, or HSX, a compact device that commenced operations in 1999. David Gates, a renowned expert on stellarator physics at the Princeton Plasma Physics Laboratory, or PPPL, acknowledged the groundbreaking achievements of both Wendelstein's 7s and HSX, solidifying the validity of the optimization concept. Inspired by these successes, American researchers set their sights on more ambitious projects. In 2004, PPPL initiated construction of the National Compact Accelerator Experiment, or the NCSX. This device employed a unique optimization method compared to the IPP approach. However, complexities arose in assembling the intricately shaped components with extreme precision. These unforeseen difficulties escalated costs and resulted in delays. Consequently, despite considerable progress, the Department of Energy made the decision to terminate the project in 2008. Reflecting on these setbacks, George Hutch Nielsen, the NCSX project manager at PPPL, admitted to underestimating the project's financial requirements and timeline. The NCSX experience served as a stark reminder of the inherent challenges in stellarator development, underlining the critical importance of meticulous planning and execution. One inherent safety feature distinguishes stellarators from other fusion reactors. Their magnetic fields are generated externally. This eliminates the need for internal pulsing currents, which can disrupt plasma and lead to safety hazards. Despite the challenges encountered, several research teams remain committed to exploring the stellarator concept, motivated by its inherent safety benefits. A notable example is the Large Helical Device, or LHD, in Toki, Japan, which holds the distinction of being the world's largest operational stellarator since 1998. Operational since 1998, the LHD holds the title of the world's largest operational stellarator. This behemoth of a device is a testament to the potential of stellarators as a viable path to achieving controlled fusion. Developed by the National Institute for Fusion Science, the LHD serves as a crucial platform for studying plasma confinement and behavior in a heliotron configuration, a specific type of stellarator design. Unlike tokamaks, the more common type of fusion reactor, stellarators like the LHD employ a fundamentally different approach to plasma confinement. Tokamaks rely on a toroidal donut-shaped magnetic field to confine the plasma. Stellarators, on the other hand, utilize a more complex three-dimensional magnetic field configuration, often referred to as helical. This helical field is generated by a set of intricately shaped coils surrounding the plasma chamber. The heliotron configuration offers several advantages over the traditional tokamak design. One key benefit is inherent safety. In tokamaks, plasma disruptions, sudden releases of energy, pose a significant challenge. The external nature of the magnetic field in stellarators eliminates the need for large internal currents, significantly reducing the risk of disruptions. Furthermore, the heliotron configuration boasts the potential for continuous or steady-state plasma operation. This is in contrast to tokamaks, which typically operate in pulsed mode, requiring frequent shutdowns and restarts. Steady-state operation offers several advantages, including improved efficiency and a more consistent fusion reaction environment. The LHD's design embodies the delicate balance required for effective plasma confinement. At its core lies a complex arrangement of coils. The main confining field is generated by 6 large helical coils, each shaped like a 3-lobed figure 8. These coils work in concert with a set of toroidal field coils to create the intricate 3-dimensional magnetic field configuration. The LHD also incorporates a diverter system, a crucial component for managing heat and particle exhaust from the plasma. The diverter channels waste heat and impurities away from the main plasma core, preventing them from disrupting the fusion reaction. The LHD serves as a platform for a wide range of research activities aimed at advancing our understanding of plasma behavior and unlocking the potential of stellarators for fusion energy production. Researchers at the LHD utilize various diagnostic tools to measure plasma parameters like temperature, density, and rotation. These measurements provide valuable insights into plasma stability, confinement properties, and transport processes. A key focus of research at the LHD is achieving high-performance plasma discharges. This involves heating the plasma to temperatures exceeding 100 million degrees Celsius, a prerequisite for achieving fusion ignition, the point at which the fusion reaction becomes self-sustaining. The LHD employs various heating techniques including neutral beam injection, ion cyclotron resonance heating, and electron cyclotron resonance heating, to achieve these extreme plasma temperatures. Another one of the LHD's primary goals is to explore the feasibility of steady-state plasma operation. Unlike tokamaks, which operate in pulsed mode with frequent shutdowns, stellarators have the potential to run continuously. The LHD has achieved record durations of steady-state plasma operation, exceeding 30 minutes. This continuous operation allows for a more stable plasma environment and facilitates the study of long-term plasma behavior, a crucial aspect of a future fusion reactor. In conclusion, the core principle behind stellarator optimization revolves around meticulously crafting a magnetic field configuration that effectively confines plasma. Achieving this ideal shape necessitates substantial computational power and intellectual prowess, a feat only made possible by the advent of supercomputers in the 1980s. The pursuit of fusion energy through stellarators exemplifies the perfect synergy between scientific ingenuity and technological advancements. Clean energy on the horizon. Stellarator reactors utilize the power of magnetic fields to control and confine superheated plasma, harboring the potential for limitless, clean energy. Every breakthrough in design and engineering brings the dream of fusion energy closer to fruition, fueled by the unwavering dedication and brilliance of researchers across the globe. Germany's recent progress in nuclear fusion research has garnered significant industry attention. Notably, the Max Planck Institute for Plasma Physics has been at the forefront of advancements, pioneering the Wendelstein 7X stellarator. This intricate reactor embodies the attempt to replicate the sun's energy production on Earth, offering a beacon of hope for a future powered by clean and limitless energy. The engineering marvel of the Wendelstein 7X is evident in its design. Supercomputers were employed to optimize its complex shape, and advanced magnetic coils are utilized to confine the plasma. Recent tests have yielded promising results, achieving temperatures exceeding that of the sun's core while exhibiting minimal heat loss. While challenges persist, this progress serves as a glimpse into a potential future where clean and safe energy becomes universally accessible. The road towards practical fusion energy may be long and arduous, but ongoing research efforts represent crucial steps on the path to a sustainable and carbon-free energy future. What do you think will be the future of nuclear fusion? Will Germany continue its lead in the industry, or will countries like Japan step up even more? Share your opinions in the comment section below. Like the video if you enjoyed it, and don't forget to subscribe to the channel before you head out. Thanks for watching. Catch you in the next video.